Okay, so jumping in Module 6, where we left off in class, we had just finished Experiment 6.2. So the biggest takeaways of this is that you need to understand that to cause rotational acceleration, a force must be directed perpendicular to the line from the axis of rotation to the point of the applied force, okay? And this imaginary line is called the lever arm. So make sure you understand this. The length of the imaginary line drawn from the axis of rotation to the point at which the force is being applied. That's the definition of the lever arm. And then it talks about how it's easier to induce rotational acceleration the farther the applied force is away from that axis of rotation. So the further you are out, the easier it is to apply it. So when you use a smaller wrench, if in the experiment you use a small wrench, you can't get the nut to move because the applied force is more effective at indicating rotational acceleration the farther it is from that axis. So you need a longer wrench, right, in order to do it. So how do we sum this up with the concept of torque right here? The tendency of a force to cause rotational acceleration. The magnitude of the torque is equal to the length of the lever arm times the component of the force that is applied perpendicular to it. And this is a really important formula that you need to know right here. Okay? And it kind of explains it in this figure. And I want to mention right up here, this is really important. Okay? So torque is the rotational equivalent of force, basically. So when you're trying to cause translational acceleration, you use a force, right? And the more force that's applied, the more translational acceleration will happen. But when you're trying to analyze rotational acceleration, you don't look at force, you look at torque. And the more torque that is applied, the more rotational acceleration that will occur. This is a really important concept to get from this chapter. All right, and then right here, again, the magnitude of the force applied to an object determines the amount of translational acceleration, and the amount of torque applied to an object determines the amount of rotational acceleration. So basically, they're just highlighting that you really, really need to know. All right, I want to look at on your own 6.5. It says a father and daughter are trying to change a tire on the car. The father attempts to unscrew the lug nuts with a small wrench, 12.3 centimeters, which is capable of applying a 612 Newton perpendicular force. The daughter, on the other hand, can only deliver a 214 Newton perpendicular force. If she chooses a longer wrench, 41.1 centimeters, is she or her father more likely to get the nut unscrewed? Okay, and then I worked it out right here. So the formula is going to be torque is equal to the force perpendicular times the distance, the radius, right? So for the father, it's going to be 612 newtons times, remember you have to convert this from your centimeters, right? 0.123 meters, and I get 75.3 Newton meter, right? But the daughter, I have 214 newtons times 0.411 meters, and I get 88 Newton meters. So even though the father's going to be stronger than the daughter's going to be able to apply more torque because the wrench that she's using has a longer lever arm. So she's more likely to get the nut unscrewed, okay? Now, of course, what's the most effective thing to do? Give the father, who's most likely stronger than the daughter, the longer wrench, right? And that's going to be the most effective way to do it. But for this problem, that's the answer. Okay, I want to note a really important part right here in this module, okay? For all problems that involve torque in this course, we're always going to assume that the applied force is perpendicular to the lever arm. Since that's the most efficient way to generate a torque anyway, it makes the most sense to work this way in our problems, okay? So just remember this for this module. This is something that they're just letting you know now. Also, in the first part of this module, we were looking at translational equilibrium, which, in that situation, the sum of the forces equals 0. And now we're going to apply the same principle when studying rotational motion, okay? So looking at this diagram right here, the top, the rod's not moving, so we're going to say it's in static equilibrium, right? There are two forces working on it, each canceling out the other. Gravity pulls it down, while the ground applies an equal force, the normal force up. And they cancel it out, and the sum of the forces is 0. So this rod is in translational equilibrium. Okay, well, what happens if you place a fulcrum underneath the rod, but not at its center over here on the side? Will it stay balanced? No, it's going to fall over, right? So think about why it's going to fall. Okay, is it translational motion? No. The rod is still in translational equilibrium when the fulcrum is placed underneath it, because the same two forces are still at play, right? Gravity is still pulling down on the rod, and the fulcrum still exerts an equal normal force that opposes the gravity. The rod, when it tilts and falls, is not experiencing translational motion. It's experiencing rotational motion. The fulcrum is the rod's axis of rotation, right there, right? And the rod's going to rotate around that point. So this rotation is cut short when the rod hits the ground, right? Nevertheless, while the rod is tilting and falling, that part of it is rotational motion. So the rod can't stay balanced because it's not in rotational equilibrium, okay? Well, why isn't it in rotational equilibrium? Your book tells you right here. Well, the sum of the forces acting on the rod does indeed equal 0, but the sum of the torque acting on the rod is not 0. Okay, so when the fulcrum is placed under the rod has the opportunity to rotate around the axis of rotation formed by this fulcrum. And then if the fulcrum is not placed at the center, gravity has a longer lever arm on one side of the rod than it does on the other, right? So the side of the rod that it will fall farther from the fulcrum, right? That side has more torque acting on it than the other side will. So the rod tilts toward the side that has more torque. And then right here, it talks about rotational equilibrium, the state in which the sum of the torques acting on an object is 0. So that's similar to the first part of this module, just applied to rotational. All right, another important concept when solving these problems that you need to know is that torques that cause clockwise motion are considered negative torques, while torques that cause counterclockwise motion are considered positive torques. So when you're working through problems, remember that torques that cause counterclockwise motion are going to be positive, and torques that cause clockwise motion are going to be considered negative. All right, let's look at On Your Own problem 6.6. Two children play on a seesaw. One weighs 221 newtons and sits 1.12 meters away from the seesaw's fulcrum. If the other weighs 171 newtons, how far from the fulcrum must she sit in order to balance the seesaw? Okay, so the first thing to do is to determine the axis of rotation. In this problem, it's easy. It's the fulcrum, right? Okay, so now that you know that, you can concentrate on the torques involved from the boy and from the girl, right? So if the girl weren't present, the boy's torque would cause the seesaw to rotate clockwise, right? So therefore, his torque is going to be negative, right? We just talked about that up here. So for the boy's torque, we're going to get negative 221 newtons times the distance, 1.12 meters, and I get negative 248 Newton meters. Now for the girl is going to be counterclockwise, right, motion, so it's going to be positive. So I get that torque is going to be 171 newtons times x, because I don't know how far away we're trying to determine that. And then I know that adding these up is going to equal 0. So I have negative 248 Newton meters plus 171 newtons times x equals 0. Well, if I just simply move it over and then divide, I get x is equal to 1.45 meters. And that's the answer for this question. She's got to sit 1.45 meters from the fulcrum. Let's look at On Your Own problem 6.7. In a physics experiment, a bar is balanced on a fulcrum. A 3.0 kilogram mass is placed on the bar 45 centimeters away from the fulcrum. If another mass is placed on the other side of the fulcrum 75 centimeters away, what is its mass? Okay, in order to get this to balance. All right. So On Your Own 6.7. So one of the first things we need to do is I need to get the force, right? And you guys should know how to do this by now, but it's going to be 3.0 kilograms times 9.8 meters per second squared, and it's going to be 29 newtons. Okay, well, what's happening on the other side? I don't know yet because I'm trying to get kilograms, right? All right. Also, it gives us the distance to the fulcrum in centimeters, and you need to be able to change that to meters. So right here I did that. It's 0.45 meters, and over here it's 0.75 meters. Okay. So the torque right here, exerted by this guy, it's going to be positive, right? Because torques that cause counterclockwise motion are going to be positive and clockwise motion are going to be negative, right? Okay, so I've got torque equals, I've already figured this out, 29 newtons times the distance, 0.45 meters, and I'm going to get 13 Newton meters. Okay, my torque over here, let's say that this is, I'm going to say that the kilograms is weight because I don't know what it is yet. So this is going to be negative torque, right? So my torque over here is going to be negative weight times 0.75 meters. Well, we know that when we add these up, the sum is going to be 0. So 13 Newton meters minus weight times 0.75 meters equals 0. Well, when I solve, I'm going to get 17 newtons. Okay, is that exactly what they asked me for? No, they asked me what the mass is. Okay, so I know that force is equal to mass times the acceleration due to gravity, right? So it's going to be 17 newtons divided by 9.8 meters per second squared, and I'm going to get 1.7 kilograms, and that's going to be the weight of this guy right here. All right, so now we're moving into objects on an inclined surface, right? So in the past, when dealing with Newton's second law, we were talking about situations that were resting on a surface and that surface was horizontal. But here, we're going to be talking about problems in which the objects are resting on a surface, but it's not horizontal. So instead, it's inclined, right? Like think of a skier. It's pretty easy to analyze these situations because there's a trick that makes it easier. Okay, so just like you always separate the vectors into their horizontal and vertical components when things are this way, when it's on an inclined surface, we're going to do the same thing, but not in the horizontal and vertical dimensions. Okay, so just as you can split vectors up into any two components, as long as they're perpendicular to each other. So when we're dealing with inclined surfaces, the best dimensions to consider are the ones in which something's actually happening. And so in this example, the skier in the illustration doesn't move horizontal. Instead, he moves parallel to the inclined surface. So that dimension is interesting to us. So that's one that we're going to be looking at. And also, if you're interested in friction, you have to determine the normal force, right? So by definition, the normal force is perpendicular to the surface that the skier is on. So the dimension perpendicular to the surface is also interesting in these problems. And let me turn the page and we'll continue. And then just notice that the two dimensions we just mentioned are perpendicular to each other. So you can split up vectors into components that exist in these two dimensions, and they're going to be useful for these problems. Okay, so we're going to split vectors into components that are parallel and perpendicular to the inclined surface. Okay, and then your book talks about the complicated geometry that exists in order to work all of this out. But basically, this is what they want you to know. When you have the parallel component, it's going to be weight times sine of the angle. And when you have the perpendicular component, it's going to be weight cosine of the angle. Okay, so right here, the component of an object's gravitational force that runs parallel to an inclined surface is equal to the weight of the object times the sine of the inclined angle, and the gravitational component perpendicular to the surface is equal to the weight of the object times the cosine of the angle. And just like you memorized before, this is just something you're going to need to memorize for inclined problems. Okay? All right. For time's sake, I do want you to read experiment 6.3, but I'm not going to do it. Basically, after you read it, you read your book and see what they wanted you to do. Basically, the thing that you're going to learn from it is that problems involving an inclined surface can be tough, right? But you also learned that when objects are on an incline, using the parallel and perpendicular components of the gravitational force, that's the best way to solve these problems. And that's what we're going to do. When we do that, we end up with the dimensions that have all the interesting information that we need, and that's how we're going to be able to solve our problems. All right, let's look at On Your Own problem 6.8. A 45 kilogram block slides down an incline that is tilted at an angle of 45 degrees. If the coefficient of kinetic friction between the incline and the block is 0.30, what is the acceleration of the block? Okay, so the first thing we're going to need to do is determine the forces, right, that are happening. So we have in the perpendicular dimension, we will call, we're going to have the normal force, right, and the perpendicular component to gravity. So I'm going to call the normal force positive and the force perpendicular to gravity negative. Okay, this is my force diagram, by the way. I've got my angle, I've got my friction, I've got the weight times sine right here. Then I've got my normal force, and then I've got my perpendicular to gravity. Okay, so if we're looking at the gravitational force, we're going to need to get the weight, right? So the problem gives only mass, but you can calculate the weight. We've done this a few times, but it's going to be 4.4 times 10 to the second newtons, okay? So for my normal force, it's going to be, here's my formula, right? I take my normal force, and then I take my force here, and then I equal them to 0. So I'm going to get 4.4 times 10 to the second newtons times cosine of the 45 degrees, and I'm going to get 3.1 times 10 to the second newtons. Then I can solve for friction, right? It's going to be 0.30. I have my coefficient, they give it to me, times 3.1 times 10 to the second newtons, and I get 93 newtons. And then I can look at the parallel dimension, okay, now that we've done the perpendicular dimension. So I'm going to have right here my weight times sine of my angle minus friction is going to equal to mass times acceleration. So we got 4.4 times 10 to the second newtons, right? We talked about that previously, times sine of 45 minus my friction, 93 newtons. And then I'm going to get 45 kilograms times my acceleration, and that's what I'm looking for, right? So then when I rearrange and solve, I'm going to get 4.9 meters per second square. So the block's going to fall down the incline, and it's going to be positive, right? Because that's how I labeled it, at an acceleration of 4.9 meters per second squared. All right, so so far we've only applied Newton's second law to a situation when there's only one object, but we're going to start looking at applying Newton's law to more than one object at a time. Okay, and your book walks you through example 6.6. I'm not going to do that. We're going to keep going. We're going to look at on your own problem 6.10, and then we're going to move into practice problems and review problems. But it says a girl is dragging two boxes, 322 kilograms and 245 kilograms, with her bicycle. The two boxes are attached to each other with a thin string that can only withstand a tension of 45 newtons before it breaks. What is the maximum force that the child can exert with her bike without breaking the string? Ignore friction in this problem. Okay, so we need to break this down into the two boxes. Okay, so the rear box, you're going to have the weight, you're going to have the 45 newtons this way, and you're going to have the force normal. Okay, so then the sum of the forces, right, is going to equal to mass times the acceleration. So I know that 45 newtons is going to equal the mass. They tell you the mass, and we're looking for acceleration. So I can solve for acceleration. All right, then I can look at the front box. Okay, so if this is 45 newtons, we know that this is going to be negative 45 newtons, right? So I'm going to get my force plus negative 45 newtons, and it's going to equal to the mass of the box times the acceleration, which we just figured out. So the maximum force that the girl is going to be able to pull with is going to be 103 newtons. Okay? All right, so I want to work through the practice problems for module number 6. Question 1 says, a 675 Newton acrobat walks on a tightrope. The woman's weight makes the tightrope sag so that it looks like this, and then they give you the picture. What is the tension of the rope on each side of the acrobat? Okay, so if you look at the forces acting on this tightrope walker, there's going to be 3 of them, right? I talk about it right here. But there's going to be gravity pulling down the tightrope walker right here, while the tightrope pulls her up from both sides of her foot. So you're going to have T1 and T2, right? And I also put the angles right here. So the angle of rope T1 is going to be 3.7 degrees. T2 is going to be 176.3 degrees. And the way that you get that is it's 180 minus the 3.7. And then the weight vector is going to be all that plus 90. So it's going to be 270 degrees. Okay. Since the tightrope walker is not falling, right? This is going to be a static equilibrium problem. So the sum of the forces in each dimension need to be 0. So you split the force vectors up into their components and solve that way, right? Okay, so for the first one, for T1, I'm going to do the T1x component, and it's going to be T1 times cosine of 3.7 degrees, which is just going to give you 1.0 times T1. Then you're going to do T1y, which is going to be T1 times sine of 3.7 degrees, which is going to give you 0.065 times T1. Then you do the same thing for T2. T2x is going to be T2 times cosine of 176.3 degrees, and that's going to give you negative 0.9979 times T2. T2y is going to be T2 times sine of 176.3 degrees, and that's going to give you 0.06453 times T2. Then I'm going to do the weight components. Wx is going to be 675 newtons times cosine of 270 degrees, which is 0. Then my Wy is going to be 675 newtons times sine of 270 degrees, which is going to be negative 675 newtons. Okay, so then in the x dimension, I'm going to add all those up and set it equal to 0. And then in the y dimension, I'm going to add it all up and set it equal to 0. And then I'm going to substitute right here. When I do my x dimension, I know that T1 is equal to 1.0 times T2. So then when I solve over here, I'm going to substitute in for, I'm going to substitute this in, okay? So that then I can solve, and for T1, I'm going to get 5.19 times 10 to the third newtons, and that's going to be the same for both, excuse me, since T2 is equal, basically right here, since T2 is equal to 1.0, right here, times T1, they're going to be the same. But technically, T2 can only be listed as 5.2 times 10 to the third because of significant figures, but they're basically going to be the same force, okay? So that's a long problem, but you need to understand how to work that out. You're going to see problems like that. All right, let's look at the next problem. A 15 kilogram sign hangs from the ceiling by 2 strings as pictured below. What is the tension in each string? Okay, so your diagram, you've got, I labeled this as T1, I labeled this as T2, and I have my weight coming down, right? I also want to know the force. So the weight equals my mass times gravity, right? And I know that this weighs 15 kilograms. So if I multiply 15 kilograms by 9.8 meters per second squared, I get 150 newtons. That's going to be important later on. And then I went ahead and put my angles here because it just helps me to know. So T1, my angle is going to be 40. T2, my angle is going to be 155.0 because that's 180 minus the 25. And then my weight angle is going to be 270. Okay, I do the exact same thing I did in problem 1. I solve in the x dimension. You can work it out right here. And then I solve in the y. I solve for the weight, x and y component. Then the sum in each dimension must equal 0. And then you'll get your tension 1 is going to equal 150 newtons. And then to get my tension 2, I know right here after solving that it's 0.845 times T1. So when I plug that in, I get 130 newtons. So that's the tension on each string. Okay, let's move to number 3. Okay, for practice problem number 3, it says a 75 kilogram man weighs himself with a scale on an elevator. and then it gives you different questions. So the first thing to know is that the problem gives you the mass, but the scale reads the weight. So when you multiply by the acceleration due to gravity, you're going to get the weight as 740 newtons right here, okay? So 75 kilograms times 9.8 meters per second squared is going to give you 740 newtons. So question number 1, what weight does the scale read when the elevator is stopped? So that's what it's going to read, 740 newtons. B, what weight does the scale read when the elevator is rising at a constant speed? It's going to be the same, 740 newtons, right? So when it's rising at a constant speed, the scale is still in translational equilibrium because the acceleration is going to be 0, right? So the equilibrium is dynamic, but it's still equilibrium. All right, C, what weight does the scale read when the elevator is traveling down and speeding up with an acceleration of 0.95 meters per second squared? Okay, so if the elevator is accelerating, the scale isn't in translational equilibrium anymore. So we have to sum up the forces and set them equal to mass times acceleration, right? So the scale exerts a normal force pointed up, which is what it reads, and gravity pulls the man down, right? So those are the only two forces acting on the man. And their sum must equal to mass times acceleration. So right here I have the force normal minus the weight, right, is equal to the mass times acceleration. So force normal minus 740 newtons is equal to 75 kilograms times, and they give you this acceleration of 0.95 meters per second squared, but we know it's negative. Okay, so my force normal is going to be 670 newtons. And that's my answer for C. D, what weight does the scale read when the elevator is traveling up and slowing down with an acceleration of 0.95 meters per second squared? They give you the exact same acceleration as part C. So it's traveling up, but it's slowing down. So the acceleration is still negative, so the scale is still going to read the same as C, 670 newtons. Hopefully you guys understand that. All right, problem 4 is a simple plug and chug. If a mechanic is exerting 97 Newton meters of torque on a nut and is applying a 415 Newton force perpendicular to the wrench, how far away from the center of the nut is he grasping the wrench? And you just take your formula, and it tells you 97 newtons per meters of torque is equal to 415 newtons times your radius, right? How far away it is. So when you plug and chug and divide, it's going to be 0.23 meters. All right, problem 5. 2 children balance on a seesaw. If the boy weighs 352 newtons and sits 1.12 meters from the fulcrum, how much does the girl weigh if she must sit 1.34 meters from the fulcrum to achieve balance? Okay, so this is a rotational equilibrium problem because in order to balance, the seesaw must be in rotational equilibrium, okay? So the sum of the torques are going to equal 0. And to look at the torques, we must look at all the forces that are acting in this problem. So remember, we said in this module that we're going to ignore the weight of the seesaw. So if you do that, there's only 2 forces that you're going to be thinking about, the weight of the girl and the weight of the boy. We're going to assume if the boy were on it by himself, then it's going to tilt counterclockwise. So the torque of his weight, we're going to say is positive. And then since we have both the lever arm distance and the weight, we can give a number for that. And then the only other force is the girl. And so we're going to say that hers is negative, right? So she's going to tilt it clockwise. All right. So for the boy, we're going to say that it's 352 newtons times 1.12 meters equals 394 Newton meters. For the girl, we don't have her weight, right? That's what we're trying to determine. So we set up the problem, and she's going to be negative because we already defined hers is negative and the boy's is positive. And then we have the distance, right? And then we solve, and we're going to get 294 newtons. Okay, so we take the boys and we take the girls and we set them equal to 0, right? So we take 340 Newton meters plus what the girl is going to be, hers, and then we solve it out and we get that she's got to weigh 294 newtons. All right, number 6. The captain of a ship holds the steering wheel and exerts 211 newtons of force with each hand as shown below. How much total torque is he exerting on the ship's steering wheel? Okay, so the problem asks for the total torque, and each hand is going to apply a torque. So what we need to do is we need to add up the torques that each hand causes, right? That's applied by each hand. And then the sum will be the total torque that's applied. Okay, so we take our formula right here, and it's 211 newtons times, and we have the distance right here, right? 1.10 meters. And so if we do that, we get 232 newtons per newtons meter for each hand. And then both hands move the wheel clockwise, so we're going to call them both negative. Okay, so we're going to do negative 232 newton meters plus negative 232 newton meters, and we're going to get negative 464 newton meters. And that's the answer for number 6. All right, number 7. A physics experiment is done in which 3 masses are used to balance a bar in a fulcrum. 2 masses, 21 kilogram and 12 kilogram, are placed on one side of the fulcrum, 12 centimeters and 21 centimeters away respectively. Where must the third mass, 18 kilograms, be placed in order to make the bar balance? Okay, so if it's balanced, all the torques are going to equal to 0. Right? And then remember, as previously stated for one of the other problems, we're going to ignore the weight of the bar. So the force is the weight, not the mass, right? So we're going to do that for each of them. So for this one, it's going to be 12 kilograms times 9.8 meters per second squared. And this one is going to be 121 newtons because of sig figs. This one is going to be 21 kilograms times 9.8 meters per second squared. And I'm going to get 210 newtons. Again, sig figs. And the third one, I'm going to take 18 kilograms, right over here, times 9.8 meters per second squared, and I'm going to get 180 newtons. Okay. So then over here, to get the torques of the 12 kilogram is going to be 100 newtons times the distance, but I can't use centimeters. I have to change it into meters. So it's going to be 0.21 meters, and that's going to give you 25 newton meters. This other one, the 21 kilogram one, is going to be 210 newtons, which we just figured out right there, times 0.12 meters, and that's going to give, I can't really read my writing, 25 newton meters, I think is what I said right there. Hopefully that is what it is. In just a second, I'll see. And then over here, to get the torque, it's going to be, remember, if I define these as positive, this has got to be negative, so they balance out. Negative 180 newtons, and then times x. I don't know my distance, right? And then I'm going to take all those and set them equal to 0. So I'm going to take 25 newton meters plus 25 newton meters minus 180 newtons times x equals 0. So I'm going to add these together, move it to the other side, then I'm going to divide and solve, and x is going to be 0.28 meters. All right, hopefully everyone can see what I did. All right, I'm going to skip 8 and 9 and go straight to 10. I'm kind of running short on time to get this video to you guys. So it says 2 boats, 0.45 kilogram and 0.32 kilograms, are tied together with a string. A child sits in the bathtub and pulls the lead boat with a force of 3.1 newtons. Ignoring friction, what are the acceleration of the 2-boat system and the tension in the string that connects the boats? So the best way to do this problem is to consider the boats individually and look at the force for each one. So this boat right here, you're going to have the tension of the string. And then over here, there's going to be 2 forces acting on it. You're going to have the tension here, and you're going to have the force of the 3.1 newtons, right? So here, with the tension of the string being the only horizontal force on this boat, you're going to have tension equals 0.45 kilograms times the acceleration, okay? And then over here, you're going to have negative t, right? Negative of what that is, plus 3.1 newtons is going to equal 0.32 kilograms times your acceleration. So if I take this equation and I substitute for t, 0.45 kilograms times acceleration, this is what I'm going to get right here. Negative 0.45 kilograms times acceleration plus 3.1 newtons equals 0.32 kilograms times acceleration. And then when I solve that out, I'm going to get my acceleration is equal to 4.0 meters per second squared. Okay, but that's not the only thing it asks for. It says, what are the acceleration and what is the tension in the string? So then I have to take my acceleration and go back to my formula here and do tension equals 0.45 kilograms times 4.0 meters per second squared, and I get 1.8 newtons is going to be the tension in the string. Okay. All right, I'm going to go over the review questions for Module 6 real quick. Number 1, what is required for an object to be in translational equilibrium? Remember that the sum of the forces acting upon that object must equal 0. Number 2, distinguish between dynamic equilibrium and static equilibrium. Okay, remember that both dynamic and static equilibrium have no acceleration. But in dynamic equilibrium, the object is moving with no acceleration. And in static equilibrium, the object does not move and again has no acceleration. Number 3, what is tension in physics? With what unit is it measured? Tension is the force from a tight string, rope, or chain, and it is measured in newtons. Number 4, which of the following situations will result in the most tension in the two strings? That's going to be situation B. In situation A, the tension in the strings aren't fighting each other, they're only fighting gravity, whereas the tensions of the string in situation B fight both each other and gravity. More force is going to be greater tension. Number 5, what is the difference between torque and force? Force causes translational acceleration, and torque causes rotational acceleration. Number 6, what is required for an object to be in rotational equilibrium? What's required is that the sum of the torques acting on the object must equal 0. Number 7, which of the following situations results in more torque being applied? Assume the forces are equal. And you have situation A and situation B. Situation A is going to result in more torque. Why? Because the force is applied perpendicular to the lever arm. Okay, so only the component of the force perpendicular to the lever arm counts toward the torque. Since the force is perpendicular in situation A, all of the force will count toward the torque, right? In situation B, the force is slanted relative to the lever arm. So only a part of it, only the perpendicular component can count towards the torque. So which one's going to have more torque applied? Situation A. Okay, number 8. A mechanic tries with all of his might to unscrew a nut. No matter how hard he tries, however, he just can't do it. What would you suggest the mechanic do in order to get the nut unscrewed? Okay, use a longer wrench, because increasing the lever arm will increase the torque. Number 9. Before cars came out with power steering, a big car required a much bigger steering wheel than a smaller car. Why? Well, if the steering wheel is large, the driver will have to hold the wheel further away from the axis of rotation, right? The larger the wheel, the further he's going to be away, or she. This increases the lever arm, allowing the driver to apply more torque to the steering wheel and thus making it easier to turn. Number 10. When analyzing motion on an incline, why do we split the forces up into components that are parallel and perpendicular to the incline? Well, the motion of an incline always occurs parallel to the incline, and the normal force exerted by the incline is perpendicular to the incline. So those are the best dimensions to work with. That's why we split it up, because that's where all the action, that's where all the information is going to be. Okay. All right, guys, so just a few hints for your test. Please understand the problem with the girl on the bike and the boxes. There's one very similar, slightly different on the test. Understand the seesaw problem. Again, there's one very similar. Understand a box sliding down an incline and how to work that. type of problem, understand torque and what you do to increase torque, understand all the different equilibriums. Yeah, just basically make sure you understand the review questions, look at the practice problems in this video, and good luck. I sent you a previous email that tells you your timeline of when everything is due. As long as I have everything by that date, nothing will be late. Okay, hope you guys have a great Thanksgiving and holiday season, and let me know if you have any questions.